The public can't see you well because there are so many chairs. Don't hide behind this. But was and then you see it. Yeah.
Yeah, now you can see the public. Oh, Mahi's over there.
She's not sleeping yet.
Hi, Danny.
Hello, everyone. Nice to see you.
Nice to see you there.
Você pode ter mais ou menos uma inicial, só que pode estar tirando a mesma quantidade. Você prepara mais ou menos no final, se você está mais ou menos com isso. Tipo, como correspondência, como o argumento de como mas eu acho que é bom, né? A gente vai propor, a gente vai considerar. Eu quando falei, eu tenho que dar por São Paulo, não confio, que eles aleatórios. Porque eles já foram deixar para trabalhar na direção. Tudo bem que não se abre uma aproximação também. Sim, sim, não, não, não tivesse isso. Muita coisa, e daí, não sei. Okay, so it seems that everyone is here, so maybe we can start. First thing, can everyone hear me well? Online and in the audience?
Yes. Yes.
Okay. So yeah, we can maybe you can start. So first, this presentation will be recorded for those who wanted to attend but couldn't due to time schedule.
It will be made available at some point in the future. I don't know when or how, but it will be made. So first of all, thank you for being here today for this presentation of NewtonX. It's nice to finally get to meet some of you after some years spent here in Marseille. My name is Baptiste Demoulin. I've been working with Mario here for the last 4 years on the NewtonX project, so the NewtonX program, and how to rewrite it to get more performance and a better development environment. So this presentation is intended at introducing you to the developer side of this new series of NewtonX code. So I will first skim through some generalities about the dynamics and the types of problems we try to solve. And then I will show you how we developed this new version of NewtonX before getting into some of the specifics of several aspects, like how do we interface with QM codes, or how do we handle surface hopping. And hopefully at the end there will be some demonstration if we have time. So let's hope that it is the case. Feel free to interrupt if you have any question or raise the hand on the Zoom interface, and yeah, we'll have some time for that later. And the second part of this presentation will be more roundtable and discussion with some presentation from you about the general subject of NewtonX, be it the classical version or the new version, and how you intend to use or how you are using NewtonX. So let's start first with a little bit of history, and first with the kind of problems we are interested in solving. So this is just to introduce the scene of what we are doing. I'm sure we are all familiar with this kind of picture. And our main problem is to understand what happens when we excite a wave packet from the ground state to an excited state, to understand what can happen to this excited state later. So coming to here, we can have several types of phenomena, from the relaxation toward the local minimum, to internal conversion to other to states of other spin multiplicity, or on the other side with avoided crossing, conical intersection. And all these phenomena appear on different time scales at selected points of the potential energy surfaces. This means we don't have any way to really bias the kind of study we do, and this is why we want to model the dynamics of those excited states. And to do that, we have a program that's called NewtonX that everyone here is familiar with. In particular, it's a package for surface hopping non-adiabatic molecular dynamics. So the development started almost 20 years ago by Mario Barbati. And this version that you all know is now named the classical series, in opposition to the new series that I'm introducing today. So just to remind you of some of the key points about this program, NewtonX was written as a collection of scripts interfaced with programs. So the scripts were mostly written in Perl and the programs in Fortran. But this is actually general. NewtonX can read the scripts written in arbitrary languages because it's built on the system calls. It's not only a program to model the dynamics of the systems. It also contains programs to generate initial conditions, so initial geometries, velocities, to produce spectrum. We have a program that's made to handle properly the dynamics, the modeling program, and we also have a program to analyze the results with the analysis program. So I tried to roughly highlight here the main structure of this NewtonX classical series. So at the top, we have the main programs that the users are most of the time interacting with. So in green, there are the Perl scripts and programs. All those scripts share a common interface defined in the colleague Perl that allows for some code refactoring and to avoid code repetition. And most of these programs call either external compiled codes in orange here, so the init-qp to generate initial conditions, or the surface hopping and CI overlap for the dynamics part. And these programs also use external scripts. So there is a large collection of those. to run Columbus or to run analytical models, to interface with CI overlap, or to handle the dynamics like the stop sign, the PL. So we can say that NewtonX, as it is today, is a very flexible system that it's where it's very easy to integrate into. Let's study a little bit the pros and cons of this kind of approach. So the project we work here has been funded by the ERC, Subnano, and the goal of this project was to go toward long time scale dynamics and to try to reach dynamics at the nanosecond time scale. And there we can have problems that we didn't really see before. So let's start with the good side of the current status of NewtonX. The good side is that NewtonX contains all the packages for complete dynamics from spectrum to really model the dynamics to the statistical analysis later. As I said, it's also very easy to integrate new interfaces because integrating a new program is just writing a Perl script with very nicely made templates. Or to integrate a new algorithm for surface hopping is very easy because you just have to plug into the existing things. And the last main strength, I think, is a straightforward and readable output. I think it's named din.out in the current version. So it's very easy to check the status of the dynamics and to write programs for analyzing these outputs. Now let's go to the not so good side of the current status of the program. The first problem when we go to our long time scales is that the performance starts to show. In particular, we have a lot of problems with input-output operations. Given the structure of NewtonX, we do a lot of system calls to call different programs that each have to initialize themselves by reading an input file and to write some output files to exchange with the others. These input-output times will get especially prevalent when we switch from high-demand QM methods like MRCI or multi-reference methods toward either analytical models or semi-empirical or other models based on machine learning. So that's really something that's hindering the use of NewtonX for longer dynamics and larger use. Then NewtonX has evolved organically from in the last 20 years. So it means that there is a lot of, maybe not lots of, but sensible amount of obsolete interfaces. There are still specific codes for Columbus 5 and all these obsolete programs that are not used anywhere today. And that makes the maintenance and the understanding of the code harder than it should be. Coming to the output side, we have nice and straightforward outputs, but it's also a text output. And if we want to go to long dynamics, that means that every time we want to write into these text files, we have to append data to it by first reading the whole file and then appending. So the larger the file, the longer it will take. And it's also very long to analyze because it may be straightforward and available for humans, but it's not really made for machine reading. So can we improve on that? And the last main problem is that sometimes it can be hard to, it's very easy to plug into the Perl scripts due to the flexibility of Perl, but it can be much harder to plug into Fortran programs that are thought of as real standalone programs and not integrating to the rest of the code. So the idea of the project is to keep all those good parts all together by still correcting the not so good points. In particular, we wanted to do a full rewrite of the core loops to see if we can remove most of these I/O operations. But by doing this, we also want to keep very low entry barriers for external developers, so that you can still come in and plug your own code with minimal efforts. And we had to start somewhere, so I said that NewtonX classical series is a collection of programs and of methods to run dynamics from generation of inputs to analysis of results. And we decided to focus mostly on the dynamics program, because this is the one where we see the performance the most, right? We generate initial conditions just once, we analyze just once, but the dynamics, we may need to run a lot of them. So this is where the development focus has been put on. So I will now describe how the first thing we did here was to improve the development process. What does it mean? First, the first novelty we brought to NewtonX was to host the development on the GitLab. So you have the address here. It's now public, so everyone can download it and interact with it by putting merge requests or post issues there for bug reporting. It's easier on the development side and on the user side because everyone can now follow exactly what is happening currently in the code and focus on the current status of the code base. Then we also implemented a standard build system. So we got rid of the homemade make files and homemade build script, sorry. And we switched to the build system, to the new build system, Maison. First, it was Auto Tools, but it will soon be deprecated. So you will see it in the demonstration later. And last big development improvement is an accessible functional test suite, and it's accessible from the build system. So either a make check or a Maison test, just to see at every step of the development process that everything is going right. And this kind of functional test suite is also integrated to the continuous integration pipeline on the GitLab, meaning that every time we do a merge on any branch, this pipeline is run, and it will give you feedback about when whether the merge is accepted or not. I think the next big improvement is also to provide the documentation specific for developers. So NewtonX has always had a very nice tutorial and very well-made manual intended at general users. Something that was missing was the documentation for developers specifying the details of implementation of NewtonX. So now the code is documented directly from source code, meaning that we write comment to the source code, we process the source code with this Ford program. That's you can think of it as a Doxygen equivalent, but specifically for Fortran code. So it's very easy to generate the documentation and to have it in place when you're coding. I will show it to you later how it looks like in real life. There is just a screen capture here. So basically it describes all the different things we have in the code. So from modules to source files to the different interfaces listed in a very nice web interface. And we try to keep this documentation as up to date as possible. Of course, it doesn't always work, as you very well know. You are also developers and it's hard to keep the documentation in place. But still, we struggle to maintain it. It also contains some general guidelines in the README section. So here, I don't know if you can properly read it, but this website has a README section that contains guidelines about what I will talk about today. I will come back to this later on in the presentation. So we talk about rewriting the core loop, and by doing this, we switched from per/Fortran code base to a full Fortran, I should say modern Fortran code. What I mean by modern Fortran, it always makes people laugh when I talk about that, because for most of us, Fortran is old and an obsolete language. But I discovered that it's not, and it's actually a very nice language to program into, especially when we look at the some of the object-oriented inspiration. What I mean about that is that most of the modules are laid out around an object that's called a type in Fortran, with a proper constructor methods that are most of the time I try to implement it as pure functions. And so this is just a dummy example of implementation. We will see some more example later. But basically, this is how I want to shape NewtonX around these kind of types. And using it in the main code is the last two lines, we just declare and we initiate these objects as simple function calls. So it's a very object-oriented inspiration. If you already coded in Python or in C++, it looks very much like it, by being more simple than C++. Then I also make use of abstract types in two different parts. So abstract types are just types that define the shape of an interface that are meant to be extended later. So as an example here, we can define an abstract type that has a status member, right, to just follow or report errors. And then we decide that this type will be used in a real context, so with a real component here, or it can be made in a complex context, and we just replace the real component from before by a complex. And this helps because now we can define functions that operate on this main abstract type, and we don't have to redefine them for each of these. We just have to define the specifics for these two extended types. And the last bit about the modern Fortran is that we use a module organization. This is mostly to get rid about these command blocks or data blocks that we always find in the older Fortran way of doing things, that I think are now deprecated. It's very unlikely to be deleted from the standard, but now it's deprecated, so it's better to follow the new guidelines. It allows to reuse code as much as possible without having to always define external interfaces. It's much more convenient for coding. And it also comes with this object-oriented advantage that we have some containerization. So I try to get rid of all the global variables to reduce the number of side effects that can have. Just like modifying the code in one place is very unlikely to have side effects on another place that we didn't intend to. And something else is that you will see most of the time that everything is private by default in all modules, meaning that each module will explicitly export functions or variables, here again, to avoid either name collisions or the side effects. So now I've laid out some of the general principles that guided the NewtonX development. I will now focus on how does it translate into the code itself. So I will describe a little bit of the implementation of this NewtonX new series. First, I'd like to present the general workflow of NewtonX. So it's not the same picture as the first one. This is like the concept of NewtonX. What do we do when we do a dynamics? Doing a dynamics means that we start from a set of initial conditions. Then we have some loops going on where we compute new positions, new energies, new velocities, and so on, until an endpoint. And if this endpoint is not reached, then we start again the loop. So these are the gray arrows here. In NewtonX, the specificity of this loop follows, let's say, four main components. So the first is to evolve the positions with respect to some gradients. And with these evolved positions, we start to compute the energies and gradients corresponding to this new geometry. So that the first step in NewtonX is to call a program or a model to compute the new set of energies by solving the Schrödinger equation. So we implemented some analytical models in there that are done in place, but we can also call external programs, simple program like Columbus, or combination of programs like the Tinker-Gaussian interface that has been added a few years ago. The main thing to see here is that NewtonX doesn't really care about what is called. It just cares about what it should feed this code and how this code should give the information back. That's the only thing we have to care about that. And this code is essentially, these external things are essentially black box. So out of this external call, we get a new set of energies and a new set of gradients. And we use this information to compute the other ingredient that we need for surface hopping dynamics is the state coupling. And we can see three different ways of obtaining these couplings. So either the code or the method provides analytical non-adiabatic coupling vectors. And this is easy because essentially here, these parts comes a part of the blue part here. And we don't have much work to do there. But if we use TDDFT or ADC2 or all these methods that don't provide non-adiabatic couplings, we can still get the information we need, either by using a model like the Bekan couplings that has been presented, I think it was 2 or 3 years ago, that has been integrated also in Newton-X classical series. And the other way to obtain that is to go to the state overlap approximation. And that's when we read the overlap matrix, either from another external program that uses QM information to compute this state overlap. In Newton-X, classically, this is done by the CI overlap program by Hirsch. But we can also think about other ways to use this information. There is the wave function overlap program that's used in Charge, or some interface will also directly provide the state overlap matrix. That's what MOPAC is doing. So these are the three ways we have to get somehow the couplings. Provided that we can have now these couplings by combining those with the velocity, we can now go to the next big parts, the surface hopping parts, meaning that we will try to hop from one surface to the other. And if we can do that, or if we have some frustrated hopping, we will need to conserve the total energy. Sorry. Okay. We will need to rescale the total energy to conserve the total energy by velocity rescaling. Once this part is done, we have now a full frame of the dynamics, and we can write it to disk in a format that I will present later. So then we have our frame that has been written to disk, and we can decide, do we want to end the dynamics, or does it end because of some internal consistency error, right? If the energy is drifting, then we have to end the dynamics. Or if we didn't reach the final time of the dynamics, we can go back to the starting point and start all over again. So we really have these three different main steps that Newton-X is built around. How do we handle that? I designed Newton-X around two main components in the code that everything revolves around. The two objects are the trajectory object, nx_t, and the configuration object, nx_config_t. Just as a note, I will introduce that later, but it might be confusing because we always talk about time t plus dt. This t here is just the suffix I use for type definition. It has nothing to do with the current time step. It's just for type definitions. It's just a convention I chose. So it was just to make it clear. I'll come back to that again later. So these two are really the core components of any dynamics. And I think of it as Newton-X config is the input of the program, and nx_ will be the output of the program. And the difference between the two derives from that. The configuration is essentially immutable, meaning that it's read from an input file and it will never change in the dynamics. It only contains the general information, like about how we want to do the molecular dynamics and the workflow we want to use. And ideally, by looking at this config, Newton-X can decide what it should do with the dynamics, which programs it should use, and which additional things we put there to spice up our dynamics, be it zero-point energy corrections or local diabatization. The goal here is that any other part of the inputs will be related to tuning these different parts. But by just specifying this nx_config, we can run a proper dynamics. And so the trajectory object, this is the output of the dynamics, and Traj actually represents the current frame of the dynamics. So it contains information about the current time. It's a mutable object, of course, and it's used to transfer information from modules to the others, right? It's used to transfer energy from the QM part to the coupling parts. It's used to transfer population information into the surface hopping parts, and so on. So we can really think of it as also the way to transfer data and information from one module to another. Of course, it doesn't contain only information about the current frame, because sometimes we have steps that we need to do interpolation or to conserve some information from previous steps. So it also contains some history. I won't go into details on it. But the important thing is that NXTraj is the only thing in the NewtonX program that is saved on disk at the end of each frame. Meaning that every information that we want to keep and to save from a dynamics has to be stored somewhere in this Traj object, right? This is the one that's stored in the results folder later. Okay. Next important thing is the input parsing has also changed a little bit with respect to the classical NewtonX. Now we don't have anymore this collection of input files. The control.din, we had several others like columbus.par and all of this. Now everything is handled through a single configuration file that's called by default user-config.nml. As the name implies, it's a name list format. So if you're familiar in some way with Fortran, that's the standard Fortran name list format. Of course, for dynamics, we also need, as before, the velocity, geometry, and some input folder. Here, the only difference with respect to classical series is that veloc and geom has been renamed veloc.orig and geom.orig. The reason for that is to avoid name collision. I know that Columbus, for instance, used by default a geom file. And just to make it clear that this is the NewtonX starting point, I decided to add this suffix .orig to indicate that it's the starting point of the dynamics. So as I said, this is the user-config.nml is a name list format. So the options are specified like that with a section name. So here there are two sections, and xconfig, which is the only required part of this input, and other sections that will contain information about the specific part, so the tuning of the code. So here I want to specify that the printmo option from the Gaussian interface is set to 20. Due to implementations detail and related to this object orientation, I wanted to give the code. I wanted to have default values defined directly in the object definition. This doesn't go well with standard name lists for technical details. We come back to that later if you're interested. For this reason, I decided to implement a handwritten parser for this type of name list format. So the type that is used is called parser T in this mod input parser module. The idea is to parse this main file only once to populate a parser object, and the parser is actually a simple linked list. So yeah, it's re-implemented as linked lists with it's a list of sections that each contain lists of key value pairs, and that is processable. It's probably not the most efficient way to do that, but we do it only once at the beginning of the dynamics. So we don't. I didn't really care about performance here, and it's very convenient to pass information from the input file to initialize the modules. In practice, how does it work? So this is how the main programs look like. We just define a parser, and let's define the configuration of this config type I showed before. I just need to initialize the parser with a conf file. So there is an error here because this, of course, should have a name, a proper name, like user-config.nml, typically. We can check the status of it, and if we want to parse the file, then you can call parser.parse. And when this parser parse means that, okay, please read the input file and get the information from there. And then we can just initialize our configuration object with this parser as an argument. Looking at the detail of this, oh yeah, right, okay. So this is how this conf init function looks like if you want to look into the mod configuration module. This is just a bunch of set routine calls. That's set from a parser. We read the specific sections. So here we want to read the nxconfig sections. and populate this object from the conf. This member from the conf object that should have this name in the parser. So this is just a list of calls. We basically transfer information from parser to the object. And if parser doesn't contain this information, then we don't touch this object, right? The specific implementation of the set function is shown below. Okay, we only read the value into the element we want to read if this value is not undefined. And that allows us to have default values directly in the object definition while still having this nice format for inputs. Okay, I will skim through this. This is just a description of the general helper modules we have in Newton-X. So this could serve as a reference data for later when some people want to implement something in Newton-X. So there is a list of general helper modules. Usually the names are descriptive enough, and you can find this documented into the developer documentation I showed before. The only important, there are some that are more important than others. The first is the mod logger that exports this nxlog object. That's basically used to give some feedback information. It can log all of it. It can log a lot of information, so it can log, of course, messages with different logging levels. But it can also log, for instance, matrices or vectors, or it's extensible. So feel free to interact with. There are lots of modules. I just wanted this, as I said, as a reference. So this is another description. General tools for string manipulations or to print numeral types, right? This toString function is very convenient because it allows to get rid of all these format specifier in Fortran. Just call the toString function and it returns a string from any numeral type. All numerical algorithms are gathered into the mod numerics. So typically what comes from numerical recipes should be implemented there. And there is also another important module, that's the mod interface, that contains functions and routines that are used to interface with the operating system. So it could be interface with the C functions to set environment or to read the content of directories, or to share utilities to copy files around or to remove files. And most of those have several versions. So if you want to take a look at this copy routine, actually the interface understands several different calls. We can copy files directly, so copy from source to dest. We can copy list of files to a directory, or we can basically rename files, or well, this shouldn't be used for renaming, but for copying files with different names. So that can be convenient in some parts of the code. For all this, of course, please refer to the developer documentation and or ask help for on the GitLab issues. It's made for that. Just some coding conventions. So most of this information you can find it in the source code. There is the directory manual, documentation, and usage, which is our bunch of markdown files that you can read. That are also integrated to the developer's documentation. I will come back to this a little bit later again. But so just a few conventions that I already highlighted. So all objects and all objects that are made to be public should have this NX prefix to avoid name collisions with others when importing. Prefix modules start with mod and the types are suffixed with T. So typically this is what a module looks like. Everything is private by default. And of course, we always use this implicit none. This is just some Fortran shenanigans that, okay, we have to put this to not have surprises later. And I prefer to always use explicit use statements. So at the beginning of modules, instead of having a general use mod my type, I try to specify what I want to import from this module. Here again, to make it clearer, what is the origin of the different objects is used in a specific file. Coming to the side of the executables, this Newton-X series is composed of 4 different executables. So there is the NX moldin for the main Dynamics program, the one that does the heavy work. NX test is the test driver. we can use that for either testing our new things on the standard inputs of Nutanix, on the examples inputs, but it's also what I use to integrate to the test suites I showed earlier. There is an input generator, so an nxgeninf. I don't remember how it's called in the classical version, but it has roughly the same capacities of the input generator from classical series. And there is nx-restart. That is the utility to either get input files at any step of the dynamics, or to generate the restart files at when the dynamics is terminated. All of those have a command line interface that I tried to make as nice as possible. So all of these programs have an help command that shows the different flags we can use with that. I will show you that in the demonstration. Yeah, just the refactoring is not fully done yet, meaning that I'm not that happy with the current status. It works, but it could be better. So yeah, keep updated. So this was the general ideas about the Nutanix implementation, general ideas. I will now go into the details of 3 different parts that you are most likely to interact with. The three different parts are the interface with electronic structure computation. Then we'll go to surface hopping implementation, and then to how the outputs is produced by Nutanix. Okay, so if we look at the main architecture of the QM interfaces as it is done now in the version of the program, the front face of these QM interfaces is this object, nxQM item T, and this object is made visible to all other programs and modules. So it's used in the main program, NextMoldin, to propagate the dynamics. It's used in the module that handles CI overlap interface, and it's used in the module that handles the surface hopping. This object has a component that is an abstract type, come back to this, an nxQM generic T that defines the general shape that any QM interface should conform to. And each specific interface, Gaussian, Columbus, Tinker, analytical models, will extend this generic type to be included in Nutanix QM. In practice, how does it look like? Okay, so when we use this QM object here, we just create, there is a function that's called nxQM create item. So it reads the configuration and it returns a QM object based on the program name and on the method we want to use. There are some error checkers, and what we do at each step, there is a mistake here, I will correct it, sorry, but typically we update the information on the QM object with new information coming from the trash, especially the current dynamic states. So we update this, and then we call QM not update, but of course we now to run QM run to actually run the electronic structure computation. That has several advantages. All the code-specific routines are now in these low-level modules here, and the main logic is completely separated from that. Basically, in an ideal world, I know that won't happen, but no one should interact with this nxQM item T. It's made so that interfaces are only handled at this level, and this just takes care of the main logic and of the heavy lifting. So implementing a new interface is just creating a new of these files, implementing the right function, and it should work. We kept the well-known temp directory, and the general idea is that all operations in these modules are handled from this temp directory, and the QM is run in a specific folder. It's not run in the temp directory itself. We create another folder to containerize the QM run. It helps with bookkeeping later. An important information is about the QM outputs parsing. So when we run the QM job, we want to extract information from it. And for this, there is a type that's called the QM info that essentially serves as a buffer between the output of the QM and the nxtrash-T. The reason is still about this containerization. We may need to do some operation on the info on the information we read from the QM, like adapting the non-adaptive copying vectors for the phase. is just to make it more clear and to have this nice interface that this function that reads outputs has only pure inputs and one specific outputs, right? This QM info. So this is what we will find at the beginning of each read output function. This info object that's initiated from the configuration. And the typical usage is this one here again. We have this QM info that's created from this read output function. So read output is a function here that's basically the generic version of this specific Gaussian read outputs. You see that there is nothing specific to Gaussian here. We just need to call this QM read outputs. And then we have this QM transfer to trajectory. And this basically takes the information from QM info to put them in the main trajectory object. And of course, that has some flags, like if you want to update the potential energy or to give a feedback. Analytical models are a little bit different. I will probably skim to that, but yeah, the main idea is that all of these models have in common that they have a 1D type specification of coordinates, okay? And so to basically convert from the 3D geometry that's used in the main code to this 1D, instead of repeating it at each interface level, there is another abstract object that derives from this NXQM generic that's called NX analytical generic. And all analytical models derive from this type. It helps with to have consistency with other methods. And it also helps because, contrary to what happens for external code, of course, everything here is done in memory, which means we don't have the same concept of reading the outputs. And just to trick the program into thinking it does read outputs, it was easier to go through this structure. But that's not that important for now. Which is more important is maybe this slide. How do I implement a new interface in NewtonX? Let's say I have a program that's called myprog and I want to interface it to NewtonX. The process is roughly as follows. We copy, there is a template file that's a fully Fortran compatible and compilable file. So it's integrated into the build system, right? So you can copy this mod template as myprog, this kind of structure. You of course have to add this file to the build system so that the build system knows about it. There is another file, mod QM interfaces, that contain the function that creates the QM object I showed you before. So add a use statement in this module to use your module here. And you just have to add a corresponding case statement in the function and create QM interface. I may show you that a little bit later. And then, yeah, modify this myprog to implement all the specific routines. And in an ideal world, that should be all you have to do. Of course, there will be problems because every case is a specific case, but this is how it should work. And of course, this information is also available in the general documentation of NewtonX. Let's go now to the surface hopping. So here again, a view of the general architecture. The surface hopping in NewtonX is handled at this object level. So there is a solver for the TTSE, NXSH solver T, that takes as main components NXSHT, which is the configuration. So it's the equivalent of the config objects of the main code for the surface hopping. So it's essentially immutable. We also have the same concept as the trajectory object from the main code, which is now the surface hopping trajectory, which is what we use to pass information from one step to another. And there is another brush object, F holder. I'll come back to that a little bit later, but essentially, solving the TGSE amounts to solving the equations for the electronic coefficients, solving another differential equation for the phase, and determining the probabilities by generally solving another differential equation. Of course, there's a lot of differential equations that usually follow the same process to solve them. The problem is that they have different components and different requirements. So if you remember in the next classical series, there was a lot of different functions for evolving the coefficients, different functions for evolving the phase, different functions for evolving the probabilities. What I try to do is to gather, to separate again the logic of solving a differential equation from the actual implementation. So there is an integrator module. I think there is a slide about that later, but that essentially takes function defined as f generic. function generic, and each of these objects derived from this type. This f holder is just like an object to create arrays of this abstract type. In practice, how does it work? Just an example of code. So we need to create the solver at the first step. And then we just transfer information from the main trajectory object from the dynamics that I call trash. So we set information like the new geometry, the new velocities, the new energies. And then we just need to run the solver with this output as a component. So this is what I talked about, this integrators library, generic integrators. So this work on when we look at how we solve differential equations, we only need a few basic components, right? We need the current coefficients. We need information about the derivative of these array functions. And if we want to integrate that to typical solver schemes, we need a way to get the derivative. So the abstract type just defines these few core components. And of course, then having defined this kind of shape of my object, I can use it to this integration scheme. So for example, the butcher integration, that's the default one. Of course, if we're at a low step, we use a second order. And else we use the butcher that takes as arguments these functions that you see is arrays of this f order, right? In Fortran, we cannot define arrays of abstract types, but we can define arrays of objects that have abstract type as components. It's convoluted, I know, but it gets easier when we get used to it. So this is how the integration is implemented right now. Okay, it's just a description of the main trajectory object. I will probably skim through that, but you see that we just have the main coefficients, the phase, and the probabilities, with the components that are coming from the main dynamics. And it's used, okay, with object-oriented again. So this was just to show a little bit of the implementation details. Okay, this describes the main solver, how we solve the TDSC in Newton-X. Okay, so we just prepared the interpolation. We perform this linear interpolation here by setting the velocity and by computing the increments of the different quantities. Then we compute all the derivatives. And then so we have this SH integration or local derivatization, depending on what we want to use, the surface hopping algorithm. And of course, if we have some hopping or frustrated hopping or something, we rescale the velocity, so we can rescale it in some direction or in the momentum direction. And we also need to adjust afterward the increment to the velocity. So, okay, just details. And how do we get information from this object? As all components are private, there are a bunch of accessors, functions. So the population is actually these get populations. Of course, there are much more details in the documentation and in the code. I hope it's way clearer than it was in the past, especially in the previous versions of the NS. I hope now it's in a good state. For the decoherence and hopping points, I gathered all the information coming from the decoherence scheme to the mod decoherence module. Two processes are currently provided: the energy-based decoherence and the orbital-based. With different levels of integration to the main code. And for describing hopping points, there is this object that essentially serves as to be printed later to give feedback about the hopping points. We'll come back to that in the demonstration. Okay, so just a few words about the output in Newton-X. The main output is still written in the results folder, exactly the same as the CS. It's hard-coded, we cannot change that. We currently provide two backends. The first is text files, and we switched from the human readable text file from Newton-X CS toward a collection of files for easy manipulation. Basically, we now have a proper geom.xyz, that's the trajectory. Each information is specified in its own file. So velocities have its files, energies have their files, and so on and so forth. We also provide outputs in the binary HDF5 format. That's the big news, and that's all the text output problems I talked about before. The other change is that all output is now written at once at the very end of a step, and not as it was in classical series where the output was written at the different step. This helped to keep consistency between what's written in output and what is actually happening in the dynamics. And as I said before, the only thing that's printed is the contents of the trash T. If something is not in trash T, it has no chance in being written in this output folder. So these are implementation details. Of course, it's handled by different type of objects. And every quantity has its some granularity with flags that you can specify in the input file if you want to print geometry velocity. Or if you want to print an adiabatic couplings, you have to specify print an adiabatic couplings equal true. But usually we don't need to do that. It's handled by the default are fine. The binary outputs, we have some, yeah, okay, so it's derived from the H5MD. That was adaptation from HGF5 to the molecular dynamics. You can refer to this paper for more details. Basically, we have two main components, one to define the file and the other one to define the H5MD elements, which are the time-dependent elements, right? We have the time series here. So we have to stack matrices after one another in this file. And the layout of the file is specified in mod IO. So the file format is specified in mod H5MD, but the layout of the file is in mod IO because this is specific to Newton X. And we have this bunch of functions to create the particles group, the observables group. These are specific to H5MD, so please refer to the paper, or we can discuss about it later. Okay, the picture I showed you is not quite complete now because I'm not that happy with the current implementation. There is a too tight integration between these modules and Newton X. I really like it to be separated. First, the first advantage of doing that would be to be able to share this file format with others for doing analysis or for other programs. Like for emulator, for instance, would greatly benefit because we wouldn't have to code the same file formats in two different programs. Also, it's impossible to operate on file while writing, which is a big hindering for using this HGF5. I'm working on that. My last project is to implement this file as a C library to benefit from the single writer, multiple reader mode that allows operating at the file at the same time we are writing it. The inspiration comes from T-Rex.io. I referred you to this, which is T-Rex is actually an initiative funded by the ERC to bring together codes in the strong correlation field. Okay, so let's maybe have a demonstration. First, I'd like to a few words about the conclusions first. We have two different ways of shipping Newton X. The dev version is the master branch of the GitLab. Then we also have a release page that you can download the point versions. I didn't talk about the result analysis, but this is now outsourced to the Ulandin package that was written by Max here in our group, but that's now handled by Mateusz. And we are also preparing a collection of all these packages. Of course, I only talked about the dynamics program. The initial conditions still come from the classical series, and we intend to prepare this Newton X package that you can download and install in one click. That contains the initcond, what I presented, Ulandin, and some other utilities like PySoc or CI overlap. Of course, I talked about it a little bit, but the idea is also to have a possible export of Newton X to have a more library-like structure to ease sharing ideas and sharing data. In the future, maybe we can do a use Newton X or an import Newton X from Python. That's a possibility. That's still open. The last point is okay. I added that because that's a very long-standing problem in my implementation. It's what to do about internal coordinates. For now, there is a large Perl library that's included, and that's solely for the purpose of generating internal coordinates. So I'm really open to suggestions here. I'd like to thank Mario for his for having me here and for his trust with this kind of projects. I could really explore and experiment with different ideas in this code, and that was really great a very great learning experience. I would like to thank the ERC for funding and all the people in the Light and Molecules group for extensive testing and bug reporting. And okay, thank you for your attention. We can do a demonstration in 5 minutes after the question, maybe. So yeah, thank you. If someone has any question, discussion, remarks, they will be welcome.
Yeah, maybe just a quick question. So now you're doing everything in Fortran. So you do all the file parsing in Fortran as well.
Yes. Yeah. It's full Fortran, so yeah, it's maybe not ideal.
Okay.
It's cumbersome at first, but now that all the interfaces are there, it gets easier. It gets way easier.
Yeah. Okay.
It was a one-time effort, but now it gets easier.
Okay.
Okay, there were. Okay, so there was this message from Pablo. So the developers doc, is it available somewhere online? Not yet. It is intended to be at some point. So when we have a proper when we release the package, we will probably also put this developers help online. For the publicity of the code, of course, Git allows for not for having private branch inside the main repository, but what we usually do is to maintain our forks on the next and push our modifications from the forks to the main branch. This is explained also in the wiki, in the developers documentation. I will show it to you now. Let's try to do that. Just generating it. Okay. Okay, it's there. Right. I think you can now see the developers documentation. So how does it look like? Maybe I can zoom a little bit more. Right. So this is the documentation, how it's intended to look like. So there are information about how to contribute. So you see there is the Git, how to interact with Git, with forking, adding an upstream and all this kind of things. So it's explained, if you want to keep your code private before publishing it, there's no problem, right? Just maintain your own private fork on X.
But is that online, the thing you're showing? So where do I find this online?
From my own computer. So it is intended to be put online at some point, right? Probably in the Nutanix website. So it will be there. It's just not yet. You have to generate it on your local version, right?
Okay, because I mean GitLab has all these like really powerful ways to generate documentations and post them online, but I guess you haven't done that yet. But...
Yeah, it could probably be integrated to the pipeline, for instance.
Okay.
That's my idea. I talked to you about this README section. So this is where you can find not information related to the source code, but to more general. Okay, so there is a few how to contribute to Nutanix, some development guidelines, and right here, implementation of new interface. So what I told you about implementing new interface is integrated into this documentation in maybe a nicer form and more details. So yeah, you are free to explore all these elements.
Just a quick comment, Baptiste. I agree, Felix. This type of thing should be better in GitLab than in the Nutanix website, because these are talking to the developers, and the developers are in the GitLab.
It is also in the GitLab. The information about contributing and so on, it's also available as Markdown files, right? They are integrated in the GitLab, so you can look at them in the from the GitLab repository. I don't know if that's clear. You won't have this nice website stuff, right? But you can look at the individual files, and they will look probably exactly like that on the GitLab as well.
I have the GitLab open. It looks exactly like that.
This one, right?
Not this one. Wait.
Yeah, you can. maybe try here.
Yeah, it's under manual documentation usage, but there's a lot of files.
Okay, so where is it?
It's
Next.
Yeah, it's next.
Okay, so everything is
Manual.
inside manual, documentation, usage, and right, system implementing new interfaces. Okay, here it is. What's probably missing for now is a link from the README to these individual pages. I completely agree that the README is a little bit missing right now. I definitely have to come back to that.
So there we go, new issue.
Hmm?
There we go, a new issue.
Exactly. Yeah, there is a new issue in the to post in the GitLab. Okay, so if there are no other questions or comments, maybe I can show you like a 5-minute demonstration about what we do in NewtonX, how to run NewtonX, how to install it. Let's with this. Okay. Where's my terminal? Okay, so yeah, I hope that you can see my terminal screen and that it's readable. So I will just go to download the code first. Where is it? Okay, so let's NX demo. Right. So I'm just downloading the repository. Let's also go there. Yeah, I just need to do something else for now because the Mason build I talked about is not the default one. It will be the next version that should come out probably very soon next week. As it's not the default in the current master version, I just need to fetch the right branch. Okay, and check out this. Right, okay. So this is the current code status. NewtonX still relies on an environment for some of its operations. So this information will be in the slides, right? I will add it later. So I need to export this environment NX home, which is the place where NewtonX will be installed. So I decided to install it in my local folder into this NewtonX NS demo folder, right? I just export it. I'd like to show you also the HDF5 capacities. So let's just have this HDF5 module loaded. I don't know how it is on your system, but on mine, I just load the module. And now the interesting part, I just invoke Mason setup with a specific prefix. And I just say that I want this HDF5 built, HDF5 built in a build directory. Okay, so it works. So you see that I have these dependencies on BLAST and LAPACK, just as the previous version. And this build directory was created. It contains some free information of the build system. Now I can just compile the code directly from the top level. Let's try it. Compile in this build directory. So the big advantage of Meson with respect to other tools is that it does an automatic dependency detection, and it can parallelize very efficiently the compiling process. So it's much faster with Meson than it was with for those who already use the make and make install version. This one is much faster. There are lots of warning. I'm really sorry for that. They should probably be. We should probably get rid of that, of some of those. Some are not really useful, but yeah, it doesn't look nice. But for our purpose, it will do. And then we can install the program. And if we now look at what the content of this NX home, we have two folders: the bin that contains the executables, so the 4 executables I talked about, and the share that contains the examples folder, mostly that contains all the example inputs, and it's also used by the test suite. So let's try to maybe run a dynamics. And for that, I will use Columbus as an example. So I just let me load the Columbus module. I copy the right set of input files from examples. So I go to Columbus. I know that this one works with surface hopping, so this is why I'm using it right now. Okay. So you see the different set of inputs I talked about. So there is still this geom.org, verilog.org that are completely equivalent to the Nutanix CS. The job NAD is still there with the same contents. Wave function.imp is also there, right? If it is present, its content will be read as starting points. And let's explore a little bit this user config file. So it has this mandatory section in xconfig, and a few other to tune the algorithms. Okay, so nothing really new here. Now I just have to, okay, let's run the program. I have everything required, NX molding. I talked about this help interface. So all the programs have this this kind of helper that tells you which options are available. But we can probably just run the dynamics. Okay. So yeah, the dynamics is running. This is the content of the log file. So this log file is really intended as direct feedback of the dynamics. You shouldn't rely on that for doing any analysis later or. And of course, it doesn't work. Ah, yeah, right. I see. That's a big mistake of my part. I have to specify somehow the environment where to find the CI overlap executables. Sorry about that. I just wanted to show you the use of the clean keyword. Okay, now it should work again. But yeah, as I said, this is purely for getting feedback about the current status of the dynamics. It's not used for anything others, right? So so let's wait a little bit. Okay, so the computation is over. It prints some timings at the end. We can see that there is one real hopping event. So nothing much more interesting here. Let's look at what the folder looks like. So we still have this temp folder. Okay. As I told, all the current computations has been run in this Columbus.job, and we keep a backup of this folder by default. Overlap computations are also done in their own folder, keeping the main one clean. And in the results, now it's much more populated than in CS. As I told you about, now if you look at the geom, this is a purely XYZ file that's directly loadable into VMD, for instance, to visualize the dynamics. I talked about the hopping points what's information we get? We have two files here for each surface hopping. Hopping veloc.dat contains information for the macroscopic case, the macroscopic step. So this was the velocity at the time step directly before hopping, the velocity just after hopping. And if we go to the micro version of that, this has much more detailed information about the micro steps, so the micro iteration that was going on. So it contains the velocity of on the trajectory of the TDSE, not on the classical one. And it has information about kinetic energies, potential energies before, after, and so on. And also the probabilities and random number. Okay. And the last thing I want to show is the shape of the H5 file. So there is a utility called H5dump. With n, you can list the content. Whoops. Okay, with n, we can list the content of this file. Oh, and it's open file, that's bad. Yeah, right. So we can have a dump of these files as a text form. So yeah, just to show you that this file is composed of a different group that contains different data sets with step, time, and the value, and you can list all these the components of this file with the n flag. So okay, the overview of the file is the structure of the file is this one. You can really think of it as a file system that has a root group H5MD with different parameters, and it contains two main groups: the observables that are for all the data that doesn't depend on the number of atoms, and there is the particles group that contains data that are number of particles dependent, like geometry, velocity, and so on. So okay, that was how to run Nutanix. I will add these few steps into the slides, and I will share them a little bit later. So if there is no question about that, maybe we can switch to the next part of the webinar with the presentation from you.
I would have a short question. Maybe I didn't completely follow, but is there anything left in Perl in Nutanix right now? Or what are the parts that are still in Perl?
Formally, yes. You will find the Perl directory in the GitLab for two reasons. The first is for handling, I think, the interface with the Tinker Gaussian 16. For technical reasons, I didn't properly test it, so I prefer to keep the Perl interface. I changed it a while ago, but still. The other thing is, as I talked about for internal coordinate generation, there is a part in the input generation process where we ask the question, do you want to generate internal coordinates? And it was done in Perl in Nutanix CS. I tried many times, like once a year probably. I set myself the goal of generating internal coordinates, and then I found out that it's way too complicated and I don't want to enter this. So I just give up. But yeah, I think it will be, we will get rid of that and redirect people who want to generate internal coordinates to other means, because it doesn't, for me, it doesn't make sense to keep a huge Perl library just to generate, just for these very specific points. But yeah, this is open to discussion. But all the programs now don't call Perl, it's really pure Fortran.
Okay, thank you.
So do you use the Columbus tools for internal coordinates? And it's int_c.x?
Yes, part of it is based on that, but yeah, we also create the internal coordinates from Perl library, from the chemistry Perl library. Oh, okay. I have to get back to that, but yeah, one idea would be to use the Columbus one. Okay. Okay. Yeah, it's been a while that I didn't get into it in the details, but yeah, I think that if we can direct people to the Columbus program, then it will be easier, definitely, because it's not nice to program, and if someone has done it before, then yeah, let's use it. Okay.
May I have a question?
Yes, sure.
I just am curious whether you did any preparations in the structure of the code to include the spin orbit couplings. That means the individual splitted components of triplet state to be included and so on, whether it's in some way prepared or whether one will have to really modify your main dynamics module and the propagation module in a deeper way.
I don't account for spin in the main parts. There are some components that are prepared for dealing with spin, for integrating with unrestricted methods. I know that there is a possibility to specify a number of alpha electrons and beta electrons, for instance, for sure. I haven't tested that because I didn't have any input files. I just kept as it was from the classical series, but I didn't retest. So there is a foundation somewhere in the code, but it probably needs a lot of polishing for being usable.
In the future, we would be interested to implement the MD with spin orbit couplings also in the new version of Newton X. I will have hopefully a new postdoc in a couple of months who could work on that, so we can get into contact then.
Yeah, we need to talk about this is typically the thing that will change deeply the structure of what we need to do, so it's better to discuss about these kind of problems.
I just a comment about that. I have the feeling that now it's going to be much easier to integrate than it was with Newton XCS. There it was too convoluted. It was really difficult to do, but now it's going to be more straightforward.
Actually, Marek has partly rewritten the spin orbit code to not be so involved, to be more following the structure of calls of the quantum chemistry codes from the older Newton X. So I asked him before he leaves our group to finish actually implementing this properly in the current classical Newton X.
May I ask you a couple of questions?
Yeah, sure.
First of all, it's about this output tool that you have implemented in this new Newton X. That's this unformatted file. First of all, can I put a verbose to Newton X to not print any formatted file, just this kind of file, to save disk space?
Yes, there is a flag that's. These are the things that we are modifying right now. But there is a flag in the Newton X input that's use text outputs. If you set it to false, the program will not produce any text files.
Okay, and
if you compile with HDF5 supports.
And another thing, can I compile Newton X without this H5, I don't know the name, packet, so in such a way that, okay, I don't have this packet, I cannot produce these files, but I can produce the formatted file as a standard file.
It's completely optional. It's possible, yes. And by default, if you don't specify anything, HDF5 support will not be enabled.
Okay.
So you have to explicitly say it so that it's enabled.
Thanks. And the last question is about, okay, did you have some comparison between the computational time required to perform like similar calculations with the old versions of Newton X and this new version? Because I don't know, I don't know how fast it is I/O in Fortran that it's known to be not so fast, and you are using like I/O in Fortran now. I don't know how
Yeah, we had a comparison. It was we had a published a paper 2 years ago. Two years ago, we did this kind of comparison on the most on the best case, basically, which was on analytical models. So
Okay.
now analytical models, everything is done in memory, and the only time you communicate with the system is writing the files. And in
Okay.
this case, for this use case, it's 2,000 times faster, right? So the new version is 2,000 times faster.
Okay, but then you don't have I/O. You don't have
Uh,
to read the information for external files. You do everything.
Right.
The...
I have another I have another input about that. When I decided to get rid of all the Perl from the new Newton X,
Mhm.
I did some test cases with Gaussian, I think, and I could reduce the time of computations by like 20% or something like this.
Okay, nice, nice. Thanks.
So that's really that's an improvement. I think it was worth it.
One main reason for the improvement comes from the fact that Baptiste moved the interpolation procedures from the Perl loop to a Fortran loop. So now the interpolation is done in the Fortran, and then whatever you need interpolation is much faster. So it affects when you use non-abatic couplings, because with non-abatic couplings always use interpolation, but doesn't matter so much if you do local dabatization, because for local dabatization you don't have interpolation. So you gain a lot for non-abatic couplings, but you don't gain so much for local dabatization.
Okay, thanks.
Mario was leaving.
No, he was asking to go outside.
Yeah, she has to stay in the office still. It's not break time. Okay. Okay, so maybe we can switch to the next part of this webinar. So if you have anything to present or to discuss about, I don't know who wants to start. Someone has something.
You're the chair. You should say who is going to start.
Yeah. Okay. I just need to. Okay. Who's the first on my screen? The first on the screen. Maybe Thomas, you can start. You're the first on the screen.
Okay. Okay, I try to share my screen. Can you maybe enable screen sharing?
No, it's not share screen. They are advanced options. We can share
all participants. Okay, nice. Okay. You can start sharing when someone else is sharing. Okay, so that should be all right.
Okay, share.
Thanks.
Okay, view full screen. So can you see my screen?
Yes.
Okay, great. So good morning, first of all. My name is Thomas Niehaus. I'm from Lyon in France, and I would like to talk about, oops, that's not perfect. I would like to talk about a bit the plans that we have. So the motivation for this is an IUF project, so Institut Universitaire de France, that I submitted, which will be rejected very likely. And this is about periodic boundary conditions in Newton X. So we would like to move a little bit away from molecules to non-abatic dynamics on molecules and go to materials. And the motivation is that we would like to understand the full chain of events that you can have with excitons in solid-state systems. For example, the creation of local excitons, charge transfer excitons, then the decay, the dissociation of excitons, so that you separate them into electron-hole pairs. At interfaces, for example, you could be interested in diffusion of excitons in a molecular crystal, for example, and then finally into the decay. And I think the surface hopping approach is a very nice way to have a comprehensive view of all the effects that happen in such systems. So that's the primary idea, and for this you need periodic boundary conditions to describe a condensed matter system and material. Of course, you need adapted electronic structure methods to be able to give you all the required inputs for a surface hopping simulation. And we personally are very much interested in this DFDB method. I don't know if you know about DFDB. It's an approximate DFT way of treating things which can do bigger systems, because for these materials you have very large unit cells. So we would like to use TD, DFDB, and so far the ground state works pretty well for periodic structures. So we get reasonable band gaps with a long-range corrected density function base type binding. And for the excited states, we have access to not only the energies, but also to analytical excited state gradients and also to the non-adiabatic coupling vectors analytically. So that works for finite structures, but we have reasons to believe that this also works for periodic systems. Especially if you are just interested in gamma point calculations, the routines that we have should work right out of the box. That means we can do periodic systems, get excited states of a solid, that means excitons. We have the gradients available and the non-adiabatic coupling vectors. So all the ingredients that you need for surface hopping in principle are there. So what are the required changes in Newton X? So this is not completely thought through. Question is, for example, does Newton X need to know at all that the electronic structure method does a periodic calculation? Well, you can think about possible changes for the MD engine in Newton X. For example, that if you move an atom out of the box, it re-enters on the other side, such trivial things. But I think the changes to Newton X are really, really modest, if there are changes at all. There's one thing, we can calculate the non-adiabatic couplings analytically. We don't need to do that from wave function overlap from different time steps. And I saw in your presentation that you already have the machinery to really read existing non-adiabatic couplings and not do it by overlap, because that would speed up the calculation, obviously, enormously if we can do that analytically. There is one additional thing. We have the vectors. We don't only have the couplings. That means we can rescale the velocities maybe in a more physical way, and that needs to be implemented, right? How to do the update. Maybe you have already routines for that in cases you have the non-adiabatic coupling vector. Yes?
Thomas, do you allow me a question? Do you have the couplings are only between excited states or also with the ground state?
With everything is there.
Okay.
Then a thing that becomes more important for materials compared to molecules might be the fact that we have to account for trivial crossings, because they will appear much more often than for molecules. With trivial crossings, I mean that not due to symmetry, but just accidental degeneracy of states that can lead to very strange things in the dynamics. Maybe, for example, that an excitation hops from one side of the system to completely the other side because of accidental degeneracy. So that's something we need to worry about. And we would like to work a bit on decoherence corrections, because these seem to be very important in general, but also for materials. So the required changes in Newton X, as far as I see it right now, are really, really modest, because we are working in the beginning just at the gamma point. So we are not looking into the dispersion of excitons, which would require possibly more elaborate changes. So then maybe also Newton X needs to know about K-space. But right now, I think everything can be done without any big changes. So that's what I wanted to show, that are our ideas for the future and how we would like to use Newton X for material simulations.
Okay, so
can I just make a comment about, so for trivial crossings, actually Newton X is the local diapletization method. So, you know, it turns out that it's very easy to find the trivial crossings if you have wave function overlaps. So then I mean, I think, for example, Shark has like these options where you would run the dynamics with local diapletization and overlaps, and then you can still do the momentum rescaling with the non-adiabatic coupling vectors. So that's one way where you kind of get the best out of both worlds.
Okay, yeah, we have to look into that. So Shark.
Yeah, in the latest development, this was also what we want to favor, right? To use local diapletization to propagate the time-dependent Schrödinger equation, but to rescale velocities with non-adiabatic coupling vectors when they are available. So that's something we are researching here in the group. I don't think it means a lot of modifications to the Newton X code in the current status. From what we looked at, it could be possible with very small changes in Newton X. So that won't be a big trouble, I think. The other part, yeah, I'm more worried about worried, it's a big word, but it's about this periodic boundary condition. Yeah, this is something that Newton X is completely unaware of, and as it does propagate by itself geometries, in principle, it doesn't need to know which kind of computation the QM is running. It should be completely obvious to what you use. Like if we talk to Tinker or whatever, we don't care if there are periodic boundary conditions there. But as we have gradients, and as you say, what happens if we cross the box and these kind of things? Maybe we need to think more about that, and maybe it doesn't have any influence, but I can't tell for sure.
Yeah. So how I see it, because the periodicity is all handled by the electronic by DFTP, which knows exactly about the box, which knows exactly about the fact that atoms moved out of the box, and it could also deal with the fact that that in the XYZ file, for example, to make it transparent, that the atom moved out of the box, that wouldn't harm any DFTP calculation. So, and it will give you the force on the atom, including the neighboring effects of all the other atoms, and including full periodicity. I think DFTP handles that quite well, and I don't think actually that Newton X needs to worry about that.
Yeah, probably not.
Of course.
Yeah, the way to do that would be to implement it as if Newton X doesn't care and see what it gives.
I have a question, and because I'm interested in the same sort of problems, and I've been thinking for a while about the comparison between localized and periodic calculations, and my concern here is more like what sort of physical situations we are representing here. Because, okay, as you are doing like DFTV, you may be able to do like big cells, and so you are, but you are in a way repeating the dynamic in every repetition of your crystal. And my question here is to what sort of systems this is a good approximation. Because if we think about molecular crystal, for example, the dynamics tend to be localized and tends to go through hopping. I mean, in contrast with what happens when you are working with inorganic system where you have like band transport. So, I mean, my question here is, okay, these sort of periodic models wouldn't be better maybe for bond transport than from localized crystals. I mean, and yes, I mean, they could be still a good approximation for short time scales, in the way that you don't really care too much about what's happening if your cell is big enough. But there also a concern about the times of the simulation and to what extent you will delocalize the exciton, and you cannot further modify the dynamics. And I think that the main thing here is related to the couplings between the different molecules that you have in the system. If you are looking at the molecular crystal, that I think it was the example that you show.
Yeah, of course, there is always a question of system size. So we are assuming for now that we can do the calculation at the gamma point, meaning that we don't really have a dispersion of the exciton, which is a good approximation if you make the unit cell very large. Having said that, that also means that you need an electronic structure method that can carry out the calculation for thousands of atoms, because as you mentioned in the example of the exciton hopping in a molecular crystal, so what we would look at is really a molecular crystal that contains hundreds of molecules, and that you really in the dynamics, you would be able to see the hopping from one localized excitation on one molecule to the localized excitation on another molecule, and have also the localized excitation over the complete unit cell included at the same time at intermediate steps, for example. So I think it is true that you always have to worry about the dimension of your unit cell if it's really covering the physics that you're interested to see. And I'm also sure that you couldn't do it with DFT, but I'm pretty optimistic that you can do it with DFTB. So yeah, you have to worry about the size of the unit cell. We are doing everything at the gamma point. But at the end of the day, I mean, when you deal with systems like this, where you have an interface, right? You always need to do that at the gamma point, right? So it needs to be big enough so that you really have a left side with the features of the bulk left side, and the right side, which has the bulk features of the right side, which means you have a big unit cell, and then you periodically replicate that, which is not the reality. It's an approximation of the reality, like a conventional supercell of a surface is an approximation to reality, right? But yes, you need to worry about system size as usual, but I think DFTB is a way to deal with that. It has its own problems, of course, we know about all that, but at least that part is something that you can better treat with DFTB than with DFT.
Okay.
Okay, so if there are no other questions or comments, thank you, Thomas.
Sorry, but it's just a quick question to Thomas. Thomas, if you go in this direction for local diabatization, you still need the wave function overlap. Can you get this? Because last time
yes.
I tried to have this problem of the at very short distance because you didn't have the parameters there.
Yeah, so that's in principle. So we have even in a development version of DFTB Plus, we have solved that, if I remember correctly. The other way, the trivial way of solving it, is to have additional points in our Slater-Costa tables for very short distances. That's a trivial solution to the problem, but it's not a nice solution. And in the development version of DFTB, we have now something that can do the wave function overlap in a more fancy way.
Right.
Okay, thanks again, Thomas.
Welcome.
Next in the list is Eduarda, I think.
Okay. I will Can you see my screen?
Yes.
Okay, 1 minute. So first of all, I'd like to say thank you for the opportunity to present some of the implementations we did in NewtonX. So this work I did during my PhD and with Giovanni Granucci, that's also presenting this webinar, where we implemented some Franco-Exton models applied to surface hopping dynamics. Our objective is to perform surface hopping dynamics for multi-conformal systems. Obviously, the most challenging part in this respect is the electronic problem, is to extract the electronic properties of multi-conformal systems, because it's difficult to find the electronic structure program that's able to treat like 15, 20, 30 chromophores, like such large number of chromophores. Some way that we found to solve this problem, a solution, is to try to use some divide and conquer strategy, something like this. And in this respect, we decided to use Franco-Exton models, because with Franco-Exton models, we can solve each chromophore individually and then collect the information of these individual calculations to put in a model Hamiltonian, which will provide me the information of the full system. Okay, but if you want to perform surface hopping dynamics, we need beyond the energies also perform compute the gradients and something like non-adiabatic couplings to propagate the electronic time-dependent equation. So the next slide will show more or less how our Franco-Exton scheme works. So in our implementation, first we perform a QMM calculation for each chromophore. Let's suppose that I have a dimer composed by the chromophore A, chromophore B. So first I perform a QMM calculation where I have A in the QM part and B in the MM part, and another QMM calculation where now I have the chromophore B in the QM part and the A and the MM part. In our implementation, in the first implementation we did, the QM part is described with the semi-empirical FOMO-CI electronic structure method, and it's interacting with the M part via electrostatic embedding. Then from these calculations here, we construct this Exton Hamiltonian, where the diagonal terms of this Hamiltonian are the excitation energies. Here are the excitation energies of chromophore A that extract from this calculation here. Here I have the excitation energies of chromophore B that extract from this calculation here. And then on the off-diagonal terms, I have the excitonic couplings or the electronic couplings, which will describe how the excited state of the two different chromophores are interacting among them. And as you can see here in my Hamiltonian, I don't have coupling between the ground state with the excited states here, but I will compensate it with the non-adiabatic coupling. So in our approach, can hop between the ground state and the excited states. Those hops can occur. So from the diagonalization of this Hamiltonian, you got the adiabatic energies of the multi-conformal system. And so we also needed to compute the gradients of this. And I would like to stress that for the integration of the electron time-dependent Schrödinger equation, we are using local adaptation. As what I stressed before, for multi-conformal system, it's very likely to have a trivial crossing. So it, as was commented before, it deals naturally with that. So we also compute the overlap matrix between the two different time steps. So we provide it to the code. And then just to summarize, this is the general workflow that we use. First, we perform a QMM calculation for each chromophore. Okay, then, from these QMM calculations, we have access to the energies. We can calculate the electronic couplings to put in the Exton Hamiltonian. We can obtain the gradients of the individual chromophores and the overlap matrix of the individual chromophores. Also, I need to perform MM calculation for the whole system because of my definition of the ground state energy. Obviously, all those QMM calculations for the individual chromophores and this MM calculation can be performed in parallel in order to save computational time. Then, the next step, we needed to compute the Exton the Exton properties, the Exton energies, the Exton gradients, as well as the overlap matrix of the multi-conformal systems. And so in this step here, we have all the ingredients that the NewtonX need in order to integrate the electron time dependent equation, so to propagate the adiabatic coefficients and to compute the new nuclear positions. So then the third step, the driver, in this case Newton X, read this information for this step here, and we will integrate the TD SE, and we will evaluate the Hopf probability, so determines the active state, and calculates the new nuclear geometry, and so on. So if it's not the end of non dynamics, it come back to step 1, and this is the workflow used for this extra model. We have this program that computes this step 2. It's using this step 2 to compute the extra properties that can be interfaced with Newton X. We did the interface with Newton X some time ago, and we did this interface also with TD-DFT with Gaussian, but we didn't check much on this implementation here. And just to finish, just to show an example that we use this scheme to perform, we studied this, we used that Frank-Exton model, for instance, to study this system here, where we propagate 12 trans-isobenzene units with quantum mechanics during the dynamics. We had 25 states in this calculation. You propagate it for 20 picoseconds and for this 96 and 113 trajectories. So this is one application of that model. So that's all, and thank you for your attention.
Okay, so thanks very much for this presentation of EXACT that I now finally can understand properly. Does someone has any question or comments about that? So yeah, just one remarks about the integration with Newton X. I wrote about that to you like it was 1 month or 2 months ago. I don't remember. But so when I passed to this new way of handling the QM interfaces, I wrote again some parts of the EXACT module. So we can talk about that later. I can show you and we can exchange. But yeah, it never occurred to me that actually EXACT could well be another external program that Newton X talks to, right? That Newton X talks to EXACT exactly as if it would talk to Columbus or Gaussian or whatever. It just happens that it's a program that itself calls some other modules. Do you agree with that?
Yes, exactly that, because actually, when you implement something like this, what you need to do is an interface between EXACT and the electron structure program, and interface between EXACT and the nuclear dynamics program. So the EXACT is just like another electron structure program.
Yeah, right. I try to reuse much of the Newton X QM structure interface to serve as interfaces in the EXACT module. So it was the second level of interface, but that didn't work very well. I wasn't happy with that solution, so I reverted to your implementation. So
yes,
yeah,
because I remember we tried to do everything inside the Newton X, like to put a subroutine, a modulus to calculate these EXACT properties. But yeah, it could be done as an external program that you call to provide you the information as you do for the other math. The thing is that I don't know, since you are working with big systems, you have a lot of information to read, so can you slow down the calculation? I think it would be faster if you put inside the Newton X, not call as external program.
We could check, yeah. We could do some experiments about that, because yeah, I think there is definitely room for improvements in the integration of the two, and that's very interesting because we could also try to generalize the EXACT, because in principle we could use any any QM methods
Mm-hmm.
in Exact
Yes.
and feed as long as it can do QMMM, right? Of
Mhm.
course, so not only Gaussian but Orca or other things, and to make it to make it general. I think it would be a very nice approach to this kind of problems, so to excite on problems.
Yeah, I agree. There is the other thing is that is the computation of the overlap matrix, but I think you have this program to do it, so I don't think it should be a problem. Because I remember when I tried to do it with Gaussian was not so easy.
Yeah, right. It's still not easy because there is a lot of things we have to prepare and a lot of bytes. There is a lot of bookkeeping. It's much more clear now, as it was the status when you came in Marseille, and the solution we came with was nice at the time. But when I rewrote all these parts, I think I came with something nicer now. Of course, with the experience that we acquired before, but I think it's cleaner now, at least. Not so, maybe not easier, but at least cleaner. But we can. There is room for improvement, and I think we can converge to some generalization and at the same time nicer integration. So yeah, that's definitely something to look for.
Okay, nice.
So if there are no other comments or questions, we can go to the next speaker. I think the next is Mariana.
Spoiler. Can you see my screen?
Yes.
Okay, so hello, good morning, everyone. My name is Mariana Casal, and I'm now a postdoc fellow at Professor Daniel Scudeiro's group in Leuven. And I'm going to quickly show you what we here at Leuven would like to use NewtonX for. So here we are pushing for this radiative surface hopping. The idea is very simple. Instead of computing the radiative hopping probability the way we usually do, the idea is to compute the radiative hopping probability basically using Einstein's spontaneous emission expression. In this case, we only need the energy difference and the transition dipole moments at each step, which are things that are most commonly available. The problem here is that it's the usual problem, which is that the fluorescence happens at very long time scales, and the cost can become prohibitively very fast. But some of people here in our group, Manuel and Daniel, and also Giovanni Granucci, which is also here, they have published this proof of concept that shows that the radiative surface hopping can indeed work. They did that with this molecule called DCS. Essentially, they took advantage from the fact that there are two excited state minima and then can lead to two different emissions. And they were able to recover a good agreement of the fluorescence quantum field, the simulated one with the experimental one, and also the lifetimes had a good agreement. And of course, because of the issue with the long time scale, they used FOAMU-CI as implemented in MOPAC, and they also did the surface hopping with MOPAC. But then our idea is that there's still a lot of room for improvement, and that's why we are using NewtonX for. We want to check and to see how can we spend use this radiative surface hopping with more electronic structure methods that, of course, are reasonably cheap for that. So the idea was going to go toward MNDO and the OM and OTM semi-empirical functions. And of course, I'm aware that there are some new features being implemented in NewtonX, especially for long time scales, that would be interesting to take profit from. But also it's also very convenient because there is already a working interface between MNDO, Tinker, and NewtonX that was done by Mattia Bondanza from the University of Pisa, which I also think it's here. So from our point of view, we only need to add a small part, which is the radiative surface hopping. We wanted to test that to check some early fluorescence features of the MABN, which is a well-studied molecule. And right now, what's going on is that we have indeed a first implementation that is being tested in our earlier version of the code. Is also being tested in collaboration with Joanna Jankowska from the University of Warsaw. But the main challenge here is not the radiative surface hopping per se, but MNDO, the description of the excited states. And right now, what is also going on is some adaptation from what I previously wrote to some new tweaks that Baptiste did to the code more recently. So that's it for me. This is what we're doing with NewtonX here in Leuven, and if you have any questions.
Yeah, I mean, maybe just a question. I mean, if you can do this just with post-processing. So I mean, the question is, can you run the surface hopping dynamics in real time and then hop to the ground state? Or could you just run normal surface hopping dynamics and then compute the time-resolved emission spectrum with post-processing?
Yeah. We could, but you mean just the emission spectrum? Or
yeah, I mean that's kind of the question. If let's say if the fluorescence is slower than the actual dynamics, then I mean you could run a normal dynamics and then just kind of analyze the trajectory and compute an emission spectrum after the run is finished. Just wondering if that would kind of make it easier or not. But just an idea.
Yeah, but it could also occur in the case that you run a longer trajectory than necessary.
Yeah,
if the
okay. Yeah,
happens, then you don't need to keep propagating.
Yeah, okay. Yeah, sure.
Mariana, I have a question. Can you hear me?
Yes. Second, right?
Yeah. So, Mariana, first of all, I'd like to understand why radiation is a dynamic process in the first place. If we have excited state minima, then for me it is a static problem.
Yeah, but you could have some because you're assuming that the fluorescence will only happen from the excited state minima, right? From that region, but
yes.
If you have some oscillator strength to the ground state, then it could also happen as you go toward that minima, and those more dynamical effects you don't see it, right?
But then the time scale would not be nanosecond. It would be much less than nanosecond. If it occurs during your dynamics, so it is not a nanosecond problem at all.
Indeed, yes. More toward the nanosecond, I would expect that we only need, we could use some static approach for it, what we're more interested in is like what else can we see that's more exotic in earlier regions. That would be more also interesting.
Okay, thank you.
If I may add something on top of that, indeed, in some cases you have, relaxation with the solvent, which is quite weird, or happening in different timescales. When you form, for instance, those twisted intramolecular charge transfers of that molecule we want to study. There is a controversy in the literature whether is this twisted intramolecular charge transfer involved in the emission or not. If you want to explain some sort of more advanced experimental spectra, like this time resolved emission spectra, how to explain these dynamic Stokes shifts that is observed. So for that, I think we need to go to those real in competition non-radiative versus radiative. If you want to.
So basically, you are saying that the non-radiative and radiative emission will be competing with each other.
Especially in those cases that they are competing at the same time scales.
Okay, thank you.
Yeah, just well, question from Uconex. How is going the integration of this radiative process? We talked about that a little bit last time you were there. Did you make some advances in this direction yet?
Slowly dangling my feet on it, Baptiste.
Okay. No,
Yes.
it was just curiosity because I know that we talked about that. So okay.
Yes.
That was no pressure. Don't worry.
No, I bother you so much. I need pressure.
Yeah, exactly.
Just a comment, Mariana. Nice to meet you again. We did some redundant work because we just implemented the MNDO dynamics into Newton X CS.
I saw.
Okay, I know that you are doing NES, but now so it's not so redundant because there are different versions of the program, so it's fine. But it's there as well.
Yeah.
But at least you can exchange some experience running MNDO with Newton X in both programs.
Okay, yes, sure. One question that I actually have for Baptiste, because I was not aware that there was input generator for the new series as well. So I was trying to use the classical series and XIMP. But now, and also the initial conditions, for example, I'm not sure if there is an implementation considering MNDO for the selection of the initial conditions, for instance.
All the initial conditions are still done in the CS.
But can I use now this implementation that you did for the CS to select the initial conditions with MNDO?
Yes, you can.
Okay, great.
Yeah, the input generator I talked about is just input for the dynamics generator. It will also generate. It will also select initial conditions based on the criterion. Okay, but it won't generate these initial conditions. This is still done by the Newton X CS. That will be shipped also with the package. I did try. I have somewhere, maybe in a branch, somewhere on the GitLab, a toy implementation of initial conditions for Newton X and S. But I gave up on that because I had more urgent things to do. It may come someday. It will come someday, I hope. But so it's still not there yet. But there is the input generator for the dynamic that you can use to select initial conditions from this. It was called final outputs from the HitConf, but I think it has changed, right, in the newest versions.
Yeah, by the way, people, now, if you remember well, the initial conditions for Newton X was in a file called final output. That was completely crazy. Now it's changed. It's called initial conditions, not final output anymore.
That's a bit. I just wanted to note, if you have an interface with MNDO for MNDO dynamics, we can integrate it to the Newton X and S, right? We can converge and integrate it to the master branch.
Well, I just wanted to say that actually there was then triplicated effort in the MNDO interface because we developed also interface for MNDO and for QM-MM with GROMACS. So it's in older version of the classical series which we are using.
Okay, I was not aware of that. So it's MNDO and GROMACS.
So Just as a notice, if you have anything that you program in CS that's not yet in NS, please open an issue in the GitLab, right? So that we can see that issues are not just for problems and work reports, it's also for ideas or stuff to do or stuff to discuss. I think it would be very nice to have this kind of things as issues, because then it would reduce the amount of replicated efforts. And I think, yeah, this, especially for this MNDO dynamic, that seems to gain traction. And I'm very curious about this GROMACS dynamic, this GROMACS QMNM also.
Yeah, that's
So,
true also for this. That's also true for the CS, because you have the GitLab for CS. And then if you see that there's someone working on some feature in the CS, you just don't do it again, because there was already a branch there on that.
Yeah, in general, yeah, please don't hesitate to open issues there. There is no hard limits about the number of issues we can open. So please feel free to, whenever there is something that someone wants to discuss, please open an issue. Worst case, we close the issue. So yeah, thanks again, Mariana.
Yeah, just if we happen to have access to this implementation with GROMACS, I would also be happy to take a look, because now I'm using Tinker, but as I mentioned, my issues is with the MNGO Tinker part, not with NewtonX. So I would be willing to test this as well. Thank you.
Okay. Thanks again, Mariana. And the last speaker is here. So the screen is yours.
Do you see my screen now?
Yes.
Okay. So in our group, we were in recent years interested in doing molecular dynamics also with the spin orbit effects in order to describe intersystem crossings and do some applications. For example, we studied these body pi molecules, which are used, can be used for photodynamics therapy, and after excitation to singlet, they go through intersystem crossing to triplet, and the triplet then can excite oxygen to singlet oxygen, and so on. So basically we implemented in an older version of the classic series the approach to include spin orbit couplings, actually two approaches. One which we developed ourselves, and also the three-step integrator method which Gonzalez developed in the SHARP program. Both give very similar results. We tested this on some thiophene and so on. And here, often with the spin orbit couplings, if you have atoms like bromine, which are not so heavy, you have to use a technique of accelerating the MD by scaling the spin orbit couplings by some factor, and then you get the usual populations at different scaling factors. For example, here was this 25 and 15, and you have to extrapolate back to unscaled spin orbit couplings to get the lifetimes and so on, because the dynamics would be too slow. So here, for example, we confirmed that the brominated body pies have much faster transfer to the triplet states. Then the other direction which we now are starting with is the use of machine learning for the non-adiabatic couplings, and also for the spin orbit couplings. We started first with some test on a simple molecule as this vinyl bromide, where we computed trajectories with ADC2 and with CAS-SCF to get some training sets for the machine learning. And then we employed the ML-Atom program to train the surfaces. And here you can see those scatter plots, which the diagonal line would be ideal accuracy of the fitting, and then the resulting trajectories, where you have the populations from the trajectories, or from the original ADC2 and from the machine learning. And here you can see that actually the machine learning starts to give strange results after 20 femtoseconds. And that was because the molecule has very fast dissociation of this carbon-bromine bond. Through analysis of this bond length, we have seen that independent on the method, it very fastly dissociates. The problem which we have here is actually the machine learning of the non-adiabatic and spin orbit couplings, which have basically random phases. It's possible to align along a trajectory, but it's virtually impossible to align the phases for the whole training set. And the solution, how one can avoid this problem, is to do learning of all the states at once with some cost function which tests all possibilities of the signs and finds the best match. And here I would have a question to Pavlo Dral, whether the learning of several states at once is already in the new ML-Atom available. And then we also tried another thing from the machine learning, and that's an approach to make a rotationally invariant learning of a vector quantity, like a dipole moment. There was some effort in this direction in the literature already, but we came with a very simple approach which uses canonical orientation to the main axis of inertia. And the molecule is first rotated to canonical orientation, then stored. We store the rotation matrix. The machine learning is done on the set of canonically oriented molecules, and then we always transform the estimated vector to the original orientation, and we were able to get quite nice scatter plots here for dichloroethane example. We have implemented this by interfacing Newton X with ML-Atom and with our code which implements this orientation. So that was a very brief presentation of what we did recently. Thank you.
Well, thank you for this presentation of the work you'll be doing. Is there any comments or question?
Yeah, there was comment to me, so I will reply that basically, yeah, I just remembered, sorry, I forgot to reply to your email, right? So
I am afraid so. So therefore, I am asking.
Yeah, sorry for this. I will reply to you a bit later because I had too many emails lately. Somehow I got.
But we will be also at this conference in Uppsala where you go, so we can discuss also there.
Okay, then it's even better. Then I can show you what you've done actually. And my PhD student Dina Jan, so she will go there. She was doing this work, so she can talk about this. But basically, like everyone who worked with this non-adiabatic dynamics, I was talking to many people. They had similar problems that larger training set leads to worse results. So that's also for different methods, not just the methods you used, some others. So it's indeed a problem. So you can discuss in Uppsala, but basically, I'm not sure if multi-state will solve all your phase correction problems, right? So, but we have a very good phase correction, machine learning phase correction weights, which would learn this very nicely. So the one thing that we now develop is extending MLAtom to excited states in more general, because see, you had to implement yourself all this for each state model, so that will be done more automatically.
Yeah, that's great. That would simplify the things.
Yeah. Okay.
Thank you.
Yeah, I didn't really get what is this accelerated MD? What do you scale exactly in this accelerated MD?
We scale the spin orbit couplings because if you have let's say bromine, then the spin orbit couplings are relatively small, and you would have to simulate 50 or 100 picoseconds of the dynamics, and that would be too slow. So actually, it was shown on a two-state model that the intersystem crossing speed is inversely proportional to square of the spin orbit coupling. So we scale the spin orbit couplings to have a faster MD, and we calculate the lifetimes by fitting the decay of the populations, and then we extrapolate back to scaling factor 1.
Okay, yeah, now I follow. Right, thanks. And related to that, that also reminds me that I have to update next for the latest version of the CI overlap that has been on my to-do list for more than a month now, and I have to integrate the latest modifications that you did on CI overlap to the new version.
You contacted me some time ago about some technical problems with the library for CI overlap, and I sent you the binary version. Did it work in the end, or you did not reply then anymore? So I thought it was solved.
I think it worked, yes. Mario tried to compile the CI overlap binaries, and I think it works, right? I don't know if Mario can comment if he's still there. Yeah, just a comment in between on the GitLab on the pipeline CI/CD. What I do for every new Newton-X release is that the GitLab compiles the CI overlap binaries, and they're available as a separated archive, so that for each release it's easy to find the binaries of CI overlap.
Oh, okay.
So I integrated the CI overlap and the LA library are submodules of Newton-X, but I think they're still private for now. So there is only the member of the light and molecules that can see them, which allows to do this kind of integration with the pipeline. And there I did some modification to compile it on the latest versions of Debian. We can talk about this later. It's just some very fun details about the code. But yeah, this I will do. But I think having this static library will help us a lot.
Yes, yes, sure. I can provide the static library.
Right. So we can discuss a little bit more about this. I will come back to you for the integration of the newest modifications of CI overlap.
Yes, we can solve this by emails, I think.
Yeah, definitely, or in another meeting, just more focused on CI overlap, right? So any other question or comments? If not, then I think that will end our little workshop webinar. So again, thanks everyone for your participation to the webinar. It was really a pleasure to finally meet you, even if online. So yeah, I will contact you and I will send you the slides I had for this for the workshop when I have updated and corrected all the mistakes. And I will try to release a proper version of NewtonX next, probably sometimes end of next week. So expect for the 1st of December, probably the version 3.6 now with all the things that we discussed today and all these improvements. And yeah, as I said, feel free to open issues and to write to us if you have any question or problems. Thanks again for your participation, and yeah, right, see you probably next time.
Thank you, Baptiste. Bye, everybody.
Thank you, Baptiste.
Thank
bye.
you.
Thank you. Thank you. Bye.
Very nice to see you all. Take care. Bye-bye.
Bye. Bye.
Present, apologies, stop. Wait.